Oh, and also, I'm supposed to be recording when you guys take exams too, and I forgot yesterday until about 20 minutes in, and I didn't want to turn on the recording while you're taking your exam and freak you out. So tomorrow it will be recorded. Okay, so all these questions here, they're all valid. I don't think we need to go over electron configuration. I think you should be able to go over that on your own because that's Gen Chem 1 and OChem 1. There's some other stuff here that's all very important, but the first question I want to look at is number 5. I always put a question like this on the exam, and there's always a good chunk of students who miss it, even though this is Gen Chem material. So I want to go back over formal charge. So there are 2 ways that you can do formal charge. The easiest way is you've been in OChem for, I was going to say 4 months now. That's not true. That's true normally, but you've been taking OChem for 4 weeks now, and you've seen a lot of organic compounds. The bonding schemes are probably pretty solidified in your head. So when you look at an oxygen that has 2 bonds and 2 lone pairs, does anybody just automatically know off the top of their head what the charge is on that oxygen? Is it neutral? Is it +1? Is it -1?
It's neutral.
Right. So it should be in your head by now that oxygen with 2 bonds and 2 lone pairs, that's a neutral oxygen. That's a happy oxygen. That's its bonding scheme when it has a double bond. That's its bonding scheme when it's part of an alcohol, right? That is a happy oxygen. What is the charge on an oxygen with a single bond and 3 lone pairs?
-1.
Right, that's a negative oxygen. So that is an oxygen that's been deprotonated, right? So these bonding schemes, you know them, you've seen them over and over, right? We deprotonate water, and now it has a single bond and 3 lone pairs on it, and we know that that's negative. We deprotonate an alcohol, we deprotonate a carboxylic acid, which is more what this is. There are some other bonding schemes that you're familiar with, and you just maybe don't really know that. Like carbon, when it only has 3 bonds, what's its charge?
Positive, -1.
It's gonna be positive, right? If it has only 3 bonds and no lone pairs. What about this nitrogen here? It has 4 bonds. I realize it's not part of the question, but what is the charge on an oxygen that has 4 bonds and no lone pairs?
It's a +1.
Right, that's a +1. So these are bonding schemes that you're familiar with. What is the charge on a nitrogen atom that has 3 bonds and 1 lone pair?
It's neutral.
Right. Yeah, so you guys do know these. We can also solve for it mathematically. Does anybody remember how to do that?
You take like the number of like valence electrons that it wants, and then subtract the number of like bonds and lone pairs, right?
Right. So oxygen, when we look at the periodic table, we know that it has how many valence electrons?
It has 6.
Right, it has 6. And it has 6 non-bonding electrons on it, so we subtract those. And then we subtract the number of bonds, right? And that will give us -1 as well. So 6 minus 6 minus 1 is -1. So you can also solve for this value, but it's going to be a lot faster if you just know it, right? So those are kind of my notes on this. So what's the answer to this question?
It's E. Oh, sorry, hold on, I flipped that.
Yeah.
C.
Right, so the answer to this one would be C, because oxygen 1 would have a -1 charge and oxygen 2 would have a charge of 0. Okay, the next one I wanted to look at was number 6. So in the compound sodium methoxide, there is blank bonding. I want you guys to just think about it for a second. Does anybody have any ideas?
Nonpolar covalent.
Let's draw it out. So what is the bond indicated by sodium here? What does that indicate to us?
Ionic.
Right, so there's got to be some sort of ionic bond happening. Ooh, I'm going to turn on Zoom annotations because the PDF is kind of a pain in the butt. Okay, so we know that we have sodium plus, and I'm going to draw out methoxide fully just so we can see the bonding. Methoxide minus. So there is an ionic bond between these two pieces. What else do we have? What about in this piece?
Polar covalent.
Right, so that's polar covalent. So the best answer here would be a mixture of ionic and covalent. Okay, does that make sense?
Yeah.
Oh, sorry, I lost my list. Oh, the next one I want is number 7. Whoa. Ah. Sorry, I guess I can't scroll the page while I'm in annotate mode. Okay, which of the following pairs of bases lists the stronger base first? I want to give you guys a minute to think through these. Okay, any thoughts? What should we do in order to answer this question?
Are you trying to figure out like the negativity of the charge?
I think that's going to be the more complex way. There's an easier way to compare two bases.
You try to which one's a stronger acid or the weaker acid in this case.
Right, we want to look at the conjugate acids and decide which one would have been the weaker acid because its conjugate base would be the stronger base, right? So we need to think about the pKs of the protonated versions of these. So this is acetate, right? So the conjugate acid is acetic acid. What's the pKa of acetic acid?
4.76.
Right. So we're comparing 4.76 versus what's the conjugate base, or sorry, conjugate acid of hydroxide?
H2O.
Right. And what's its pK?
15.7.
Right, 15.7. So which one is the weaker acid?
Water.
Right, water is the weaker acid. So which base is the stronger base?
It's gonna be the second one, HO.
Right, so hydroxide is the stronger base. Is this listed correctly then? No. Okay, what is the conjugate acid of azonide, H2N minus?
Ammonia,
Right, and what's the pK of ammonia?
is it 38?
Yes. And then we already did this one, 4.76. So does this have the stronger base listed first?
Yes, it does.
Yeah, B is going to end up being the answer. But we can look at these other ones as well. This repeats a bunch of the pKs we've already looked at. So we would have 15.7 because the conjugate acid would be water versus 38. So that one's not going to work out. What's the conjugate acid of H2O?
Hydronium.
Yes, and what's the pK of hydronium?
Negative 1.76 or 75.
Yep. So that shows us that hydroxide is stronger, which I hope we know anyway, because oxygen negative, right? And then iodine versus chloride. Even if you can't remember the pKs of these, do you remember which one is the stronger acid?
Fluoride.
Between hydriodic acid and hydrochloric, which one is the strongest? Which one is the stronger acid?
HI.
Right, so this has the stronger acid first, which means this would be the stronger base. Okay. Anyway, so the rest of that was just proving to you guys why B is the correct answer. Okay, are there any questions about this? We're good? Okay, my next one. Sorry?
I was just saying, yeah, sorry.
Okay. The next one that I had here is number 11. So go ahead and think about it for a second.
Is it 3?
We got to draw out, I need to think about the whole molecule. I think you're right, but I read this as carbon at first, sorry. When I first started talking, I was like, no, okay. So it's asking about carbon-carbon sigma bonds. So let's just look at just the carbon framework for a second. So we have carbon, 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 carbon. Okay, these two are obviously sigma bonds, so we at least have 2. And how many sigma bonds are in a triple bond?
1.
1. And how many pi bonds are in a triple bond? Just out of curiosity.
2.
2, right? So our answer is 3 because this is made up of 1 sigma 2 pi. I got a question in the chat about where'd that go? Number 3. I'm gonna hop up there real fast. So it says the compound methylamine CH3NH2 contains a C-N bond. In this bond, which of the following best describes the charge on the carbon atom? So the answer to this, does anybody know?
+1.
How many bonds does the carbon have?
4.
Four.
4. So it's happy. It's definitely not positive or negative.
I was looking at the nitrogen. Sorry, I was.
So then the next question is, the slightly positive and the slightly negative could only happen if there was a dipole in this molecule. Is there a dipole in this molecule? Is there a difference in electronegativity between carbon and nitrogen?
Yes.
Yeah, there is. So there is a slight dipole pointing towards nitrogen. So the carbon is going to end up being partially positive and the nitrogen would end up being partially negative. Does that make sense? Okay. The next one I had written down is number 12. So in the structure below, the hybridization of the oxygen is blank and the COC bond angle is blank. So in order to answer this question, remember that you need to think about the lone pairs, right? So what is the hybridization of this oxygen? It has 4 things bonded to it.
Is it sp3?
Right, it has to be sp3 if it has 4 things attached to it. So that gets rid of the first 3 options. The other reason that we're kind of going through this way is because your exam is going to be multiple choice. So I also kind of want to show you guys how you can eliminate some of your answer options. So then what is the bond angle that goes with an sp3 hybridized atom?
It's a 109.5.
Right. So we want to pick E, not D. And it says less than because the electron pair domains here, they're going to take up a lot more space. And so this bond angle is actually going to be a little smaller than 109.5.
120 is for planar, right?
Right. Yeah, so for trigonal planar, you would have 120. Sorry, gotta open up my list again. Okay, which of the following compounds is not a constitutional isomer of a compound with an empirical formula C3H70 and a formula mass of 118.164? So there are quite a few here. I need to zoom out. So what's the first thing that you need to do in order to answer this question?
You want to draw out C3H70.
Well, so it's giving you also the formula mass. So you need to figure out how many iterations of C3H70 there are, because that's the empirical formula. So this is kind of related to the stuff we did for mass spec. Although I'll give you a hint. All of these have 2 oxygens in them, right? So you're gonna have to double it. So what would be the formula doubled?
C6H14O2.
Right. So we need to go through and figure out which of these has the formula C6H14O2. So first, we can definitely tell that all of these have 2 oxygens, so we can't eliminate any by that option. The next thing I would go do is add up all your carbons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So then our differences are going to be in the hydrogens. You may notice that one of these has a double bond. So we can also calculate the degrees of unsaturation real fast. So how many hydrogens should a compound with 6 carbons have if it has no degrees of unsaturation? How do we
14.
calculate that? It should have 14, right? So that would be the number of carbon atoms times 2 plus 2. So our compound should not have any degrees of unsaturation. Does that eliminate any of these options?
The double bond.
Right, so B is the answer because it has a double bond, which means it has a degree of unsaturation. And if you go through and count, I'm sure all the other compounds have 14 hydrogens, and B probably has 12. Okay. Are there any questions about that? Okay. The next one that I circled is 20 and 21. So you're given a structure, and this is a really common type of question. I'm definitely going to put one like this on your final exam. Which of the following functional groups is not present in the HIV protease inhibitor drug called saquinavir, which is the compound up above?
Ketone.
Yeah. So definitely the best way to approach this type of question is to hunt for each of the functional groups that it lists off. So it says aromatic, just find one and you're out and you're like in the clear for that one. So we have one aromatic there. Alcohol, I see one here. Amine, there's an amine here and here. Amide, we have amide, 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 amide. Ketone, I don't see any ketones. Which functional group occurs more than 2 times in the structure of HIV protease inhibitor drug called saquinavir?
Amide.
Right, so we found 3 amides. I will go ahead and cross out ketone because we just said that there are no ketones. There are no carboxylic acids, so you can cross that out. And there are no alkenes either. All of the alkenes are part of aromatic systems. I know we didn't cover that in this in OCHEM 1, but there are definitely not multiple of those. So amide is the answer. Okay, number 24. Identify the correct IUPAC name for the following structures. When you're doing this type of problem, my best advice to you is to name the compound before you look at the options. Because once you start looking at the options, your mind starts thinking, oh, well, this one looks legit. That's the one I'm going to pick, right? Don't do it that way. Definitely start with the compound and come up with your own name. So we're ignoring these. What is the longest carbon chain in here?
6.
7.
I'm only seeing 6. It
Well,
has,
if you go from top to bottom, you get 7 that way.
oh yeah, so if you do this, but then you end up with a complex one here. Oh, that's tricky. Let's see if they only have one heptane name. Oh, I wouldn't do that to you guys. Let's skip this one because I wouldn't give you a complex substituent name. We'll move past this one. Sorry, go ahead and ignore this guy. Okay, look at number 25. The structures below are blank. How are these two related to each other? So the first question is, are they the same compound?
No, because the CH3 is on the same in the first one and then on different ones on the, like, separated,
Right.
I guess.
No, you're exactly right. So the structure of this compound here, remember there are 2 carbons represented here. So we can call that carbon 1 and carbon 2 behind it if you want. So that would be carbon 1 and carbon 2. Carbon 2 has a CH3 coming off of it. Our carbon 1 is going to have a methyl and a hydrogen. So our first compound is 2-methylpropane. What is our second compound here? Remembering that there are 2 carbons here.
Butane.
Yeah, it's butane. Okay, so what is the formula of 2-methylpropane?
C4H10.
Okay, and what is the formula of butane?
C4H10.
Okay, so are these cis-trans isomers of each other?
No.
Definitely not.
Are they conformational isomers, meaning just a difference of rotation?
No.
No. What are they?
Structural.
Structural, right? Structural is another word for constitutional isomers.
Quick question. Answer choice E. That's not possible, right?
Right. Yeah, answer choice E counts on students not knowing the difference between a conformational and a structural isomer. I've put this question on an exam before, and it was like 80% of the class got it wrong, which is how I ended up on this review. So the main thing that you had to realize was that you had to draw out these structures in order to get it. Okay, number 27. I love this type of question. Always put this on exams. In the lowest energy conformation of the compound below, how many alkyl substituents are equatorial? So what do we have to do to answer this question? Can we figure this out just looking at this drawing?
No.
No, what do we need to do?
Draw the chair conformation.
Yeah, we need to draw a chair. Okay, and then we need to do what?
Put your substituents onto the chair.
Okay, which substituent is our biggest substituent?
Bottom left.
Yeah, the bottom left is going to be an isopropyl substituent. Here we have ethyl and then methyl. So which one do we want to place first?
The ethyl.
The isopropyl is actually bigger because it has more carbons. So that's the one that we want to place first. So do we want our big substituent to be in the equatorial position or the axial position?
Equatorial.
Right, so I'm going to pick a place where I can put it equatorial and down. So that puts that here. Now we need to place everything else. So the ethyl group is 2 carbons that way. So that puts us on this carbon. And on this carbon here is the down position, axial or equatorial?
Equatorial.
Right. So this one will also get to be equatorial. And then the methyl group is 1 carbon over from that. Is the down position axial or equatorial on this one?
Axial.
Right, it's axial. So how many of our alkyl substituents got to be equatorial?
2.
2.
2. A lot of times students answered 3 on this one because they're like, well, ideally, all of them would be equatorial. Yes, ideally they all would be, but they cannot all be equatorial because they're cis and because of the number of carbons between them. If the methyl group had been over here, then yes, they could all be equatorial, but that's not the case. Or if the methyl group had been pointing up instead, it would have worked out, but you have to follow the actual structure that's given to you and make sure you draw the chair conformation. I do not know many organic 1 students who can do this in their head. There are some, but and maybe some of you can, but most cannot. Okay, number 29. Arrange the following Newman projections of butane in order of energy. So what are we looking for when it comes to like being, notice that it has the less than signs. So we're going from the lowest energy to the highest energy conformation. What are we looking for in a low energy conformation?
Don't you want it to be like more stable?
Yes, and what about the structure would make it more stable?
If it
The
was
2 methyls are as far away from each other as possible.
Yeah, we're spacing out our alkyl groups, and do we prefer staggered or eclipsed?
Staggered.
Staggered, okay. So which structures are automatically on the lower end and which ones are automatically on the higher end?
1 and 3 are on the lower.
Right, and between 1 and 3, which one is the lowest?
1.
1. So which answer has that? just C. All right, so this one's actually really simple. If you can just identify the lowest energy conformation, you're set. Usually I'm not that friendly when it comes to test writing. I probably would have given you a 1, 3, 2, 4, and then a 1, 2, 3, 4 option. So that you had to decide between this one and this one. Remember that staggered is always lower energy than eclipsed, even if you have your groups closer together. Okay. Rank the following carbocations in order of stability, the most stable first. How do we know which carbocation is most stable?
The most stable one is going to be the tertiary carbocation.
Right, so we're looking for tertiary is greater than secondary, is greater than primary, is greater than methyl. So do we have a tertiary one?
1.
Right, number 1 is first, so we can cross out option A and option D. And then what comes next?
3.
3. So a lot of these can just be done by like the process of elimination. Okay, number 32. This is one that really should be a freebie, and yet I always end up with a lot of people missing this type of question. Excuse me. So which line angle formula corresponds to the chair conformation below? Which ones definitely do not correspond?
1 and 4.
Yeah, why 1 and 4?
Basically, anyone where bromide's pointed down.
Because 1 and 4 are cis when in the chair conformation they're trans.
Right, so in the chair conformation, we have one that's up and one that's down. So that makes them trans, and 1 and 4 are cis. So we gotta get rid of those. Okay, and then we have 2 and 3. So what I would do if I were you is I would draw this out myself. So I'm gonna draw out a flat hexagon and draw my bromine up. And my ethyl group is 2 carbons away that way and down. Okay, so we have to do a little bit of rotating in order to figure this out, right? So which one of these actually matches this?
3.
3. So if we just rotated it 180 degrees that way, putting the bromine over here and the ethyl group here, we would end up with the right structure. Does that make sense? Okay, number 35 is another one that should be a freebie, but often trips people up. So what term describes the structural relationship between cis 1,2-dimethylcyclopentane and trans 1,3-dimethylcyclopentane? If you can't tell off the names, what is the best thing for you to do?
Draw it out.
Draw it out, yeah. So we have cis 1,2-dimethylcyclopentane. And trans 1,3. So they're trying to put something in your head by underlining cis and trans. What are they attempting to put in your head here? Does anybody know?
Diastereomers.
Yeah, they want you to think diastereomer, but what is it actually?
Constitutional isomers?
Right, these are constitutional isomers because this one is 1,2 substituted, this one is 1,3. So the methyl groups are not on the same carbons. These are not stereoisomers of each other. They're constitutional isomers. But by underlining cis and trans, it kind of makes you think that they might be diastereomers. And if it had been, cis, ooh, that was horrible, I'm so sorry. Cis 1,2 versus trans 1,2, that would have been correct. So these two are diastereomers of each other when drawn properly. Wow. But the ones that are actually in the question are not. Okay. We didn't do a lot of Fisher projections this semester, so I'm not going to put any questions like this on your exam. These two questions are very similar to the one that we just did, and I think you guys can handle those on your own. Or do you want to do one together? We can do one together because they're almost identical. So we'll do 37 together, and then you can do 38 on your own later. So what term best describes the structural relationship between 2R3R4S 2,3,4-trichloroheptane and 2S3S4R 2,3,4-trichloroheptane? The first thing that I would want you to note is that they're both 2,3,4-trichloroheptane, right? So what answers can we definitely get rid of?
They're not.
E.
Yeah, they're definitely not constitutional isomers because they are the same connectivity. What else can we get rid of?
E.
Yeah, we can also get rid of E because their structure is the same, but the letters that go with them are different. So we know that they're at least isomers of each other. Is there anything else that we can eliminate?
You can eliminate enantiomers.
I wouldn't eliminate that yet.
Conformers?
Conformers, right. Conformers just means rotation around sigma bonds. There's not just a difference of sigma bonds here, like rotation wise, if we have actual different stereochemical designations. So then the next thing you could do is write out your designations next to each other. So this is our first one, 2R3R4S. The second one is 2S3S4R. Now, what is the definition of an enantiomer?
It's like all of the substituents are changed.
Right. So if all of the stereochemical designations have been flipped, it's an enantiomer. A diastereomer would be all, or at least one, but not all, right? So which one is this?
A.
Yeah, these have to be enantiomers because the 2R got flipped to 2S. This R got flipped to S, and the S got flipped to R. So these are enantiomers of each other because they would be exact mirror images. They are exact opposites. So that's the way you deal with that type of question. So the other one you can actually do very quickly now, probably, if you wanted to take a look at it. We have 2R3R4S versus 2R3R4R.
Diastereomer.
Right, those would have to be diastereomers. So R, R, S versus R, R, R. We flipped only one of them. These have to be diastereomers. So this is one where you just have to identify the stereochemical designation. Okay, let's do number 44. I'm going to give you about 2 minutes to try and solve this on your own. Okay, are we ready? So which carbon is number 1? Is it the one with the ethyl or the one with the methyl?
The one with the ethyl.
Hmm?
Is it the one with the ethyl?
Yeah, why is it the one with the ethyl?
Is it alphabetical?
Right. So that's the first thing that can help you narrow down some options here. So anything that has 3-ethyl in it is a goner. So option A can go away, and option E. And then also, what else can we eliminate?
B.
B, because that would be numbering the long way around. We don't want to do that. So look at that. We already did some really good stuff here. What other step can we now skip based on these answers?
Naming.
Yeah, we don't have to worry about naming anymore. What else? What's the difference between C and D?
The rotation
Of which one?
of the first one.
Right. So notice that they both say 3S. So don't waste time determining the stereochemical designation of carbon number 3. So this is half review and half how to take a multiple choice exam, I guess. So once you narrow it down, figure out what the difference is, and then figure out which answer is correct. But don't waste time on confirming that it's 3S, because why, right? Why would you waste your time like that when you're trying to take a test? So, okay, let's look at only carbon number 1. I'm going to erase these numbers just for clarity. So what is the high priority item on carbon number 1?
Is it chlorine?
Mm-hmm. All right, so chlorine is number 1. And then between ethyl, the top of the ring or the bottom of the ring, what's our next priority?
Bottom?
So let's go out atom by atom, right? We have carbon, carbon, carbon. That doesn't really teach us anything. Next we have carbon, carbon, carbon. That's unfortunate as well. On this next one, we have hydrogen, we have carbon and chlorine, or we have, I lost track because I'm all in the same color. That's really unfortunate.
It's the chlorine.
Yeah, it's the top because we get there faster. Sorry, I lost track of my directions. Yeah, so there would be hydrogens on this one and a carbon. So that's, yeah, we're comparing carbon and chlorine versus carbon, hydrogen, hydrogen, basically. I know that's confusing because of the same color. Yeah, so top of the ring, because you get to the chlorine faster via the top of the ring. I'm going to erase all that because that was really unfortunate. Also, the erasing with a PDF is horrible. You have to erase every single bit of it. Okay, so this is our number 2. What's number 3?
The ethyl. Or sorry, no, the
Right.
bottom.
Yeah, the bottom of the ring. And then we have 4 is our ethyl. Okay, so this is kind of unfortunate because our low priority group is coming out at us. So what are we going to do with our stereochemical designation?
Flip it.
Right, we're going to determine it and then flip it. So we're seeing 1, 2, 3. What rotation does that look like?
S.
But it's actually
R.
R. Okay. Does this make sense? Yeah. So even if some of these topics aren't things that you necessarily need to review, I hope you're at least getting something out of the like multiple choice process. Okay. 45, 46, and well, okay, so 45 through 49, I wanted to actually put you guys into breakout rooms for a second and have you just go over these together. So I'm going to put you into breakout rooms for about 3 minutes because this honestly shouldn't be too bad.
Sorry, which number are we doing?
45 through 49. I'll give you 4 minutes. Okay, what did we decide for number 45?
We got B.
Okay, so
I
let's
got E.
E. Okay, so I think there are a couple that are pretty easy to cross off, right? Which ones are really easy to cross off?
A and C.
Yeah, A and C both have negative charges. So those are pretty easy to get rid of. Anything else?
H2O.
Yeah, we've seen H2O act as a nucleophile before. Let's look at the structure of B. We have, oops, horrible. We have nitrogen and 3 methyl groups. And there's a lone pair on nitrogen. And look at the structure of BF3. And there are lone pairs on all of the fluorines. Ooh, wow. It automatically does a dot if you hit it just right, I guess. Which I'm apparently not. Okay, what do we know about BF3? When have we seen boron used in a reaction?
Hydroboration, but that's BH3.
Right. But that kind of shows us the only time that we ever seen boron used was in electrophilic addition, right? The thing about boron is that there's going to be a very large positive with a partial negative on the fluorines. The fluorines have tons of lone pairs, but do they want to make another bond?
No.
No, halogens make one bond. So is there anything in this compound that could make another bond? No, it's actually a good electrophile. It's a Lewis acid, whereas the amine has a lone pair and actually acts as a Lewis base. So an easier approach to this question would be, are all of these Lewis bases? So go through and figure out which ones can act as a base, and that will help you eliminate B as an option. E ends up being the correct answer. Okay, the next one, consider the substitution reaction shown below. By what mechanism will the reaction proceed? So what's the first thing we notice about this?
The primary leaving group.
Right, so we have a primary alkyl halide. Is there anything that gets rid of for us?
SN1.
Yeah, definitely. Okay, and then let's look at our reagents. We have, what do you call NaCN?
A good nucleophile?
Yeah, a good nucleophile, right? Is this going to do a free radical reaction?
No.
No, we've never seen a radical reaction with cyanide, right? So cross that out. And then we have to decide between SN2 or there is not enough information to tell. We have a primary alkyl halide and what was correctly identified as a good nucleophile. I think there's plenty of information to decide that that's an SN2 reaction. What do we know about DMSO as a solvent? Does anybody remember what class this falls under?
Polar aprotic.
Right, polar aprotic. And is that good for SN2?
Yes.
Yeah.
Yep. Not that that's our deciding factor, but in case you were tempted to pick D, there is a lot of information here, right? Polar aprotic. Right, we're good. Okay, which of the following compounds is the most nucleophilic? Which one can we automatically cross off?
E.
Why B?
D.
Oh, D, okay. Yes, yeah, get rid of the boron trifluoride, like we just had this conversation, right? Now the next thing that we can do is we can compare all of the oxygen containing compounds, but what I would do first is decide between oxygen and sulfur. Between oxygen and sulfur, which one is the better nucleophile?
Oxygen.
Oxygen is the most basic, typically.
Sulfur.
Yeah, sulfur is the better nucleophile. It's a larger atom. It's going to be a better nucleophile, so it's actually just automatically A. B, C, and E are trying to get you in a trap of trying to decide between those which ones is the better nucleophile, but it's just pick the sulfur containing one. Okay, 48. Which one of the following compounds will undergo an SN2 reaction most readily? There are two factors happening here. We have leaving group and degree of substitution. Which one is the easiest one to eliminate options on right off the bat?
Leaving groups.
Right. Which has the best leaving group?
Chlorine.
Are we sure? We're comparing iodine and chlorine.
Iodine.
Iodine is the better leaving group. So cross out your chlorine options because for every chlorine option, there is an identical iodine option. So get rid of the chlorines. It's going to be one of the ones that contains iodine. Okay, and then you have to think about the structures of these compounds. So A is clearly primary, right? You don't even really have to draw that out. But if you wanted to, it has 1, 2, 3, 4, 5, and a methyl. So that'd be A. And then C would be this one. And then D looks like neopentyl iodide. Sorry, this is A, C, and D. Which one is the best for SN2?
A.
A. It's primary, so is D, but remember the neopentyl group is one of the weird exceptions to the primary thing. It typically does not undergo SN2 very easily because this is huge, right? This is completely blocking the backside attack, so it's not going to happen. We're going to pick A. Okay, 49. Which of the following alkyl halides reacts most rapidly via an SN2 reaction with sodium cyanide? What's the first thing that we can do some answer eliminating on?
The leaving groups.
Right, so which one do we prefer?
Iodine.
Iodine. So let's cross out this fluorine option. That's horrible. Bromine is gone. Okay, the other ones we have to draw out. So 1 iodo, 1 methyl cyclohexane. So we have a cyclohexane and iodine and methyl in the same one. That's a tertiary substrate. Is that going to work?
No.
No. Okay, C is iodo cyclohexane. That's secondary. And then D says 1 iodo hexane. Which one is best?
B.
D? 1 iodo hexane. Okay, did we do pretty well on these? Cool. These are definitely like common varieties of questions. Okay, we have about 20 minutes left. Are there any requests?
Can we go over chair confirmations a little bit more? I always get confused with those because I would always get confused like where to put it on the chair.
Sure. Okay, so let's do a whiteboard. Okay. So draw the most stable conformation of this compound. In order to answer this question, you want to draw a chair. And then you want to place your bulkiest groups first. So which one is our bulkiest?
The tert-butyl.
Right, the tert-butyl. Does it matter which carbon on here you put it on?
It wants to be equatorial, right?
Yeah, it wants to be equatorial, and for the sake of our own minds, let's just put it pointing down. But does it matter which carbon we actually draw it on?
Not really, as long as we're consistent.
Exactly, right. I think that's where a lot of people get stuck is they're like, well, it's here, so which carbon is that on the chair? It doesn't matter. You're in charge of the chair, right? So I tend to just pick the carbon that's going to be the easiest for me to draw off of. If I want it to be equatorial and down, it's much easier to draw that on this carbon. Why am I drawing wedges or dashes? I don't need to do that. It's much easier for me to do that on this carbon than to try to force it like over here or over here, even though like that's perfectly fine. I like to draw it on the edges when I can. So then we just have to make sure that we go clockwise or counterclockwise to our other groups. So if that one is down and equatorial, we need to go 2 clockwise to place our ethyl group. So that puts us here. Which direction does this have to go? Up or down? For the ethyl group?
Up.
Up. And is that going to be axial or equatorial?
Axial.
Yeah, that's axial in this position. Okay, and then going counterclockwise to the methyl group, that puts us on this carbon. We want to put it up. Is that going to be axial or equatorial?
Axial.
It's actually equatorial here. So remember on your chairs, the axial position actually tends to go in the direction that the chair seems to be pointing. So like this corner here, let me switch colors. This corner is pointing down, the axial position is down. This is pointing up, the axial position is up, down, down, and it just alternates from there, right? So if you can tell based on the way that the corner tends to be pointing, you can place enough of your axial positions to find them correctly. And then your equatorial positions are always going in the opposite direction of the axial. Does that make sense? So when I'm looking at a carbon and I'm trying to decide, like, you know, is the, if I want to go down, well, the axial's up, so down is equatorial. Okay, let's do another one. Okay, I'm gonna give you a second to try and draw this out yourself. Draw the most stable form and then also draw the least stable form. Okay. Let's go through this. So what is our biggest group,
The isopropyl.
right? So we need to put it pointing up, and we also want to put it in the equatorial position. So pick your favorite up equatorial position. Okay, and then I'm just going to move clockwise. So 2 over is my oxygen, and it's also going to be going up. On this carbon is up axial or equatorial?
Equatorial.
Right. That's lucky. And then next carbon over is my methyl group. Is methyl going to be down? Sorry, it's it is down. Is it axial or equatorial?
It can still be equatorial.
Right. And then 1 carbon over is another methyl group going down. Is it axial or equatorial? Axial, right. Cool. So that gives us 3 groups equatorial. Now we want our least stable conformer. Gotta do a chair flip here. And I mean, really, you could draw the chair the same way if you wanted to. It wouldn't be a huge deal, as long as you flip your axial and equatorial. So now I have my up equatorial, but if this is the least stable, so this is our most, this will be our least. Where do I want my isopropyl group? Do I want it up or down? Oh, sorry, axial or equatorial?
Axial.
And thank you for following along with me as I have a small mental breakdown, I think. Okay. And then 2 carbons over to get to our alcohol. Is that going to be axial or equatorial?
Axial?
Right. So it should be the opposite of whatever it was in the previous structure, right? Because we did a chair flip. So then we go to our next carbon. Our methyl group was down equatorial. Now it should be down axial. And then our next methyl group was down axial. Now it should be down equatorial. So this checks out. We had 3 equatorial. And here we have 3 axial. Okay. Does that help with the chair conformations?
Yeah, it helped. I don't know. I think I just need to practice it because every time I look at it, I can get confused because I'm just not sure where it's supposed to go. But you said it doesn't matter like where you start. And so after you start with like one, like so on the most stable one, you put the OH equatorial, but then you also put the methyl equatorial. So how are you able to put them both like that? You don't have to like flip flop every time.
No, you do not. So it depends on if they're up or down. And so I'm going to draw another chair and put them in slightly different positions, and you'll see kind of what I mean, hopefully. So the important thing was that our isopropyl group had to be pointing up, and we want it equatorial because this is our most stable. So I'm going to put it here because this is also another up equatorial position. Now I need to go 2 carbons clockwise to get to my alcohol, and it has to be pointing up, right? So 2 carbons clockwise is this carbon here. The up position on this carbon just happens to be equatorial. So I get to put the alcohol in the equatorial position. Now 1 carbon over clockwise again is my methyl group, and it has to be pointing down. 1 carbon over, the down position happens to be equatorial. So it gets to be in the equatorial position.
Okay, I see. So it's like that picture in the top right, the yellow and the blue.
Right.
That,
it has to be on either a yellow or blue stick.
gotcha.
And if we're lucky, more of them end up equatorial. And then the last one is methyl down. Here, that happens to be axial. So even though I started on a totally different carbon, I still end up with the same outcome, right? The same 3 groups are in the equatorial positions.
Okay, I see. That makes sense. Okay. I think I was just, the way I was looking at it, I just like, that makes a lot more sense now. Okay, thank you.
Yeah, no problem. I've taught this class, like, I don't know, 5 or 6 times, and I've been teaching some OCHEM since grad school. So like over the last 10 years, I've taught this topic several times, and it's always hard. It just is, right? It's just confusing. It seems like they're made up rules, which there kind of are, but there also aren't. Like the rules are very distinct, but then it seems very arbitrary. So yeah, it's always hard, to be honest.
Okay. Yeah, I remember like when we talked about this topic in class, I felt like we kind of just went through it really fast, and so it just didn't sit yet. Like I was still kind of confused after.
Yeah, and we didn't get time to review it because summer.
Yeah.
Yeah.
But this makes a lot more sense. Okay, thank you.
Okay, no problem. Are there any other questions? Because we have 6 minutes. We could go back to the review, or if you have any specific questions, we can do that instead. Review. Is there any other topic that you guys want to hit?
Stereochemistry.
Stereochemistry, okay. Okay, anything specific, or do you just want to go over like enantiomers, diastereomers?
Yeah, I think just the basics. I don't know. It really kicked my butt on the exam.
Yeah, that's another topic it's always hard. It just is. Anything that's kind of visual like that and conceptual tends to be one of the more challenging concepts. Okay, so let's start from the very beginning. Let's see. Okay, so let's just do a basic definition real fast. So remember that, oh, why can't I draw? Oh, okay, there we go. Okay. So we have 2 kinds of stereoisomers. We have our enantiomers, which are mirror images, but non-superposable, which means they're just not the same molecule, right? Mirror images, but not the same. A diastereomer is a non-mirror image stereoisomer. So let's draw a couple compounds here. We're just going to draw something, let's do something simple. So we have a methyl group and we have a bromine. How many chiral centers are on this molecule?
Is there 2?
Yeah, it's 2. Also, let's make them more complex. I'm gonna put a methyl group here too. So there are 2 chiral centers. How many stereoisomers do I have then? Does anybody remember the formula?
Isn't it 2? It's the number or it's 2 to the number of chiral.
Right. Yeah. So 2 raised to the nth, where n is the number of chiral centers. So in this case, we are 2 squared, which gives us 4. So we're going to draw out all of our possible stereoisomers. So one possibility, let's draw 2 where the methyl group is up. And then we're going to have 2 where the methyl group is down. Now we can have the bromine up, methyl down. We can have bromine down, methyl up. And then we have the same options here. Okay. What are the relationships between these molecules? Let's say this is A, B, C, D. What's the relationship between A and B?
Diastereomers?
Yeah, those are diastereomers. How do we know that?
Only the bottom 2 change, not the top methyl.
Right, so we kept the top methyl group in the same position and we flipped this stereocenter only. So that makes these diastereomers. Okay, what's the relationship between A and C?
They're also diastereomers.
Right, for the same reason, because the bottom chiral center is the same, but the top one changed. Okay, what's the relationship between A and D?
Enantiomers?
Right, why are they enantiomers?
Every one is switched.
Right, so we switched the methyl group from up to down, and then we switched the bromine methyl stereocenter to the opposite as well. Okay, what's the relationship between B and D?
They're diastereomers.
Yeah, I'm gonna rename this to F just because we have the letter D everywhere. Okay. So these are diastereomers because we kept the bottom one the same but changed the top. What's the relationship between C and F?
They're diastereomers.
Right. Okay. And then across C to B, what are they?
Enantiomers?
Yeah, they're enantiomers because we flipped both stereocenters. So one way of looking at enantiomers is mirror images. The other way of looking at it is changing all of the stereocenters. So remember that enantiomers can be drawn out a couple different ways. So I'm going to draw compound A. One way to draw the enantiomer of compound A would be the way that we drew F, right, where you just flip everything. The other way to draw it would be to draw a mirror plane and mirror the stereochemistry. So this also gives us the enantiomer. And if you think about taking this mirror image that I just drew and flipping it over like a pancake, like think of picking up that structure and just flipping it over, just like you could take your hand, right? You could take your hand and go like this and flip it. So my thumb was on the left, now it's on the right. If I flip it over, my flipped over structure would be F, because this methyl group that's coming up, when I flip it over, it's going to be going down. So that's how you can get that kind of relationship as well. I realize also it's 11:43, so if you need to go, feel free to go. Did that help with stereoisomers for now? Or do we want to do office hours at 1 o'clock and revisit this?
That helped a lot. It always just like gets boggled in my brain with like just even the definitions. And so, yeah, I've actually wrote all of that down so that I can look at it again.
If I held office hours at 1 o'clock, would people come? Okay, how about this? I'll be there at 1 o'clock, and if you guys want to come, you can. And if you don't want to, that's fine. We can either continue the review that we already started, or I can answer specific questions. So if you have any questions that I did not answer just now, feel free to come at 1 o'clock and I will try.
Will you be recording that session? Just because I'll be
As long as it's okay with the people who are there asking questions, yes.
Okay, thank you.
Awesome, thank you.
No problem. And then if you can't come at 1 and you have some questions, feel free to email me. All right. Bye, guys.
Bye, thank you.